Thank you very much for your kind introduction. And I have to apologize. I cannot be there in person. Today, I'm going to talk on a slightly different topic from other talks, and it's a little bit more applied. Okay. So this is a, oh, it doesn't work. Just a second. This is the first slide, but sometimes. The second slide. I have to go to the second slide. Okay, good. Okay, here's my plan. Of course, we start with motivation, and then we start with Kobayashi-Warren-Carter energy, and it's discussing its singular limit. And also, we are original problem is the gradient flow, and we are also interested in the singular limit of Kobayashi-Warren-Carter gradient flow. And this is the main issue here is the energy function always involves total variation part. And this is one topic covered in this symposium. So this is still in the scope of our this symposium, I hope. Okay, and this is my today's talk is based on following articles, which is many of them are already published, but some are unpublished right now. Okay, this is a list of authors. Okamoto is my former student. Uesaka is a former colleague, and but he is now in company. And Sakakibara is a professor of Kanazawa University now. And Professor Kuroda is a professor of Hokkaido University. The Kubo is his student. Okamoto is now the postdoc of Kyoto University. So these are member of our this project. Okay. And let us start with motivation. What is the original source? Okay, the original source is coming from to describe evolution of multigrains in the material science. But also this problem has some potential application in the image segmentation and data clustering. I'll explain. Okay, motion of phase. Okay, what is the motion of phase boundary? And here's a typical example. The domain is divided by 3 phase, 1 to 3 phase, and this E gamma is the interfacial energy, and gamma 1 2 is this part, and gamma 2 3 is this part, and sigma 1 2 these are coefficient, and this is the length. Yes, and classical setting is the sigma 1, 1, 2. These are constant, positive constants. And the motion of gamma is what is a usually gradient flow of E gamma. And E gamma is gamma J is expected to move such kind of curvature, and Mij is mobility. And this is the angle is some contact angle at triple junction. Herring condition we are often assumed. Today's talk is different. In the case, sigma j depends on the structure of the phase. So assume that each phase has some structural constant like average angle, U1, U2, U3. And assume that sigma ij depends on this kind of difference of angles. What happens? The earlier study is by Kobayashi and Warren-Carter, 2000, and they propose phase field approach, but no motion, no horizontal motion. And recent study by Epstein and Liu and Mizuno gives the interface approach, and it also not only the energy changes by this angle, but also this is moved by mean curvature. It's combined way. So it's more complicated. Today's talk is based going to this. Today's talk is related is on this Kobayashi-Warren-Carter part, not this part. So let me explain very briefly potential application. So if there is okay, we would like sometimes in the image analysis we would like to select some particular part of image, something like some specific organ, any such kind of specific object, and trying to draw the contour of particular object. And this is often for this purpose, manifold Schach functional is often used. And Kobayashi-Warren-Carter energy is very closely related to Mumford-Shah. So this is also interesting to apply image segmentation. And also data clustering is, there's some data and would like to describe by its feature. So we'd like to have such kind of line. So this is this energy also seems to be very promising for this such kind of purpose. Okay, now let me explain Kobayashi-Warren-Carter energy, and the energy is the following. This is a gradient of V. Okay, and this is often EE epsilon SMM is often called single well modica Mortora function. F of V is a single well, V minus 1 square, and alpha V is V square. It's weight plus single well modica Mortora function. And U and V is has some physical meaning, which I did not write here. U is a kind of average angle in each domain, and V is I think, whether this part is a full crystal or amorphous. If V is close to 1, it's close to completely crystallized, and if V is equal to close to 0, this is very amorphous, something like that. Okay, what is the original Kobayashi-Warren-Carter equation with epsilon is equal to 1? This is gradient flow of actually Kobayashi-Warren-Carter energy with respect to weight L2 norm, whose weight depends on the solution. It is well posed, still open problem. The difficulty is the second equation includes total variation flow, which is difficult to handle because it is degenerate and singular diffusion equation. And this is one of important topic in this symposium, I think. Oh. And okay, although this problem is difficult, especially U part is difficult, people add delta prime or mu here to avoid this part of to avoid degeneracy of V square. Delta is to avoid degeneracy of coefficient, and nu is as extra smoothness. Okay, and the global existence solution is known for such kind of settings. Right. So not exactly the same as Kobayashi-Warren-Carter. Often nu is positive. And even uniqueness is not known without nu is assuming nu is positive. So there are many, yeah. These modifications to avoid degeneracy anyhow. So I would like to say original Kobayashi-Warren-Carter system is not yet solved. What is the meaning of this quantity? U is a quantity in each grain like averaged angle. And V is order parameter. And V is close to 1. So if epsilon is small, many places V would like to be 1. And this part is ordered part, crystal part. And the other part, V is not 1, is something amorphous. And the thickness of amorphous is approximate epsilon. So the question is the following. Today we are just discussing 3 questions. What is the limit of energy as epsilon tends to 0? What kind of profile or minimizer of the limit energy? What is the limit of the solution of Kobayashi-Warren-Carter flow as epsilon tends to 0? This is a flow problem. The first 2 questions is just energy problem, and this is a flow problem. So these are my major questions, and not yet completely settled, or just the beginning stage of the theory, I think. So let me explain. Gamma convergence. Okay, we consider the one-dimensional version of Kobayashi-Warren-Carter singular modica Mortora energy. Okay, so this is easy. E epsilon, this is initial energy, and M is one-dimensional interval, and this is F of V is if I is this is single well potential, and this is double well potential, and epsilon is small parameter. This is the energy we we consider. Okay. So does the question, does a minimizer under some constraint convert to a minimizer of some limit energy? Then what is the limit energy? And there's a very natural language originally introduced by Duziorge, is that gamma convergence. And this is people here know this type of definition very well, but let me explain. There are two energy, E epsilon is defined on the set X, and if E epsilon tends E, we say E epsilon tends E in the sense of gamma, if lower semi-continuity holds, and also the recovery sequence exists. So this is any sequence V epsilon V, EV is smaller than the inf of E epsilon V epsilon. And here, V, for any V, there's a recovery sequence W epsilon, such that EV is equal to the limit of E epsilon W epsilon. So the first, second inequality guarantees that EV is not too small. Of course, this concept depends upon the choice of topology for the convergence V epsilon to V and W epsilon to V. So this is a gamma convergence, gamma limit, gamma convergence, and this limit is called gamma limit. Precisely gamma minus one limit. So, okay, and the merit of, but there are many merit of this kind of gamma limit. But if epsilon is one typical method, merit is if epsilon is a minimizer of E epsilon, then the limit U epsilon, limit of U epsilon U is a minimizer of E, provided that U epsilon actually combines to E U. So okay, one often needs to check the compactness to prove U epsilon U for some U. But anyhow, once it's converges, this should be the U should be a minimizer of E. So this is a very good. So double wave case. So if F is double wave potential, then it's very successful. E epsilon plus volume constraint, for example, volume average volume is 0. Oh, okay. So V is integral is 0. Then this E epsilon converges E in L1 sense. Gamma converges in L1 sense, and the limit is just a number of the jump of U. The limit is two value only limit energy is only finite for two value function, with of course average 0. And otherwise it's infinity, and the value is just the number of jumps plus some computable constant. And this is originally studied by Modica and Mortora, and further higher dimensional case, Modica and Peter Sternberg. So this is very successful for double wave case. So what is the problem for single wave case? Let us consider the interval -1 to 1, this interval, and E epsilon BV is equal to E epsilon V. So plus this is a single Modica Mortora energy plus BV 0. So 0 is a value of 0 at value of V at 0, and it is square, and B is a given positive function. What is the limit as epsilon tends to? And you immediately see L1 convergence to course, because if you look down in L1, this point is 0 point is just to disappear, missing. So L1 is not so good for this convergence. If you consider the gamma convergence. And here's a shape. What the shape? W epsilon. This W epsilon. Suppose that W epsilon is a minimizer of E epsilon B. This energy, E epsilon B. Then the W epsilon energy of W epsilon is smaller than the constant energy of constant function, and constant function 1 is a minimizer of F, and at 0 is 1 over 1 plus B. And this is complicated, but if you look at the picture, it's rather clear, right? So this is epsilon is large, very large, 0.1, this is red line, and this is blue, and if epsilon is small, you get this one. So you see W epsilon combines to almost, except to 0, W epsilon combines to 1, and yeah, 0 point is something like that. So it is easy to understand. Okay, this is a linear problem, so you can solve it explicitly. And that's the reason I show the formula, but we can easily see the phenomenon. So what is the suitable topology to catch the above limit? L1 is not so good. Is it possible to prove the gamma convergence under such a limit? Okay, and before going into our problem, let me explain some related problem. And there's a famous functional called Ambrosio-Tortorelli, and this is a functional E epsilon, UV, curl E epsilon, UV is something like V squared gradient U square plus lambda U minus E square plus E epsilon V. E epsilon V is the same as before. And this is the fidelity term. And what he said, what they prove is this gamma limit is a Manford-Schach function. The Manford-Schach is something like this kind of function. Of course, fidelity term is the same, but this term K is unknown set n minus 1 is a Hausdorff measure, so area of K, and except that this is Dirichlet energy. This is the gamma limit of Manford-Schach function. No. Sorry, Ambrosio-Tortorelli function. This is this kind of Ambrosio-Tortorelli approximation. So if the energy looks like such kind of area of some jump discontinuity, then it is important to consider such kind of Ambrosio-Tortorelli type approximation epsilon, because this is hard to calculate in many sense. And the brittle fracture, application to brittle fracture is, for example, by the paper by Frankfurt and Manizo, and for Steiner problem, the paper by Remenat and Santa Ambrosia, something like that. I don't have that problem today. So what is the interpretation? Kobayashi-Warren-Carter energy model is this part is a single modic motor part, the same. But this energy is not the Dirichlet, but total variation. So in some sense, this is Ambrosio-Tortorelli inhomogenization. So this is original total variation, but wait, inhomogenization of the total variation. So original Ambrosio-Tortorelli functional is considered as Ambrosio-Tortorelli inhomogenization of Dirichlet energy. So this is our interpretation of this problem. So what's the difference? In the case of curl E epsilon, the limit of E epsilon has the same depth, which implies that set K is a finite set of one-dimensional case. In the case one-dimensional, if energy is finite, K, the set K must be finite set if the problem is one-dimensional. In our case, the depth of the limit is not the same. It depends on the size of jump of U. The set K can be a countable infinite set. So countably infinity set, even in one-dimensional case. So this is different. So what is the relation to Kobayashi-Warren-Carter energy? If U is the average angle, then okay, this is just one jump. Then the energy, Kobayashi-Warren-Carter energy is nothing but E epsilon single modic motor energy plus sigma square B sigma V square 0. So this is in this particular case, it is reduced to our earlier problem. So what gamma limit under the graph convergence? It turns out graph convergence is very good for this purpose. But let's consider just for simplicity, try to avoid the effect of boundary. Just the periodic case. Let gamma be a set valued function. Okay, and gamma is a graph of gamma. Gamma is set valued, but B is a graph, and graph is compact. if the graph is the set B is a set of set valued function whose graph is compact. So bounded upper semi-continuous value function, functions. We say gamma j tends gamma under the graph convergence shortly this graph if the Hausdorff distance of gamma j to gamma is tends to 0. And if the gamma j is a singleton, then this we just write gj is gj to gamma with some abuse of notation. So what we prove is the following. Let V epsilon combines to C in B, then this limit Kobayashi-Warren-Carter energy is a limit singular modica molecular energy is such kind of lower bounded by this lower limit of V epsilon. In particular, Xi should be A0. A0 is a set that sigma Xi of X is just one, except countable number of Xi, and other places just the closed interval containing one. In our paper, the case of closed interval is considered. The behavior near the boundary is also studied, but here I just mentioned about a periodic case. And what is E0BSMM? This is so first of all, graph of Xi is something like this kind. And what is the energy? Energy is missing. This is one page missing. I'm sorry. I skipped one page. F is a single modica. F is a single well potential. And of course, this is not degenerate, we assume. And V is a square root of F tau and integral from 1 to V. And then the limit singular modica molecular and is a function such that Xi G Xi minus plus G Xi plus or Xi is A0. A0 is a set defined in the previous slide. And this is a Xi is a set variable and sometimes it's interval Xi minus and Xi plus. And this S0B SMM is just adding this minimum value of Xi A plus A is M. This is a given set. This is positive part. Okay. Then we have such kind of gamma limit result. Okay. So this is our limit. And A0 is a function such that Xi is equal except finitely countably many countable number of Xi. Xi Xi is equal to one singleton, and otherwise this is an interval. And G is the energy defined in this way. Okay, so this is the story. And the proof, let us explain proof. The number 2 is actually not so difficult. We have to be carefully chosen the connecting curve. And let us mention that infinite inequality part. By the Cauchy-Schwarz inequality, we see that this is a G. Oh, I'm sorry, this is something crazy. Not question mark is unnecessary. TVGV. The key idea is U epsilon change variable G by using G. G of V epsilon, we set U epsilon. And using unfolding of U epsilon by the arclet parameter of its graph. For function of one variable, we define this length of graph. Okay. What is unfolding? For unfolding U, we define unfolding U. For function U, we define its unfolding big U by US of U of XS, where XS is the inverse function of S of X. So the following, S is anyhow length, and graph of S could be jump, right? because U is may have jump. And the graph of U is in this case, then graph of S is like that. It is the inverse function of S is this one. So this is the important thing. Total variation U and total variation big U is the same, but the Lipschitz U is always less than 1. So using this kind of unfoldings, we have, okay, here's the picture. This is the U epsilon, and this is the limit of unfoldings. So U epsilon, unfolding U epsilon, then the limit is just this type of stuff. Right. And JXI is a interval that XS is equal to XI. So inverse function could be has a constant part. And this constant part is a connecting part. And so we have to divide the way. And yes, so something like this picture we expect. And assume furthermore FV is something also okay. Let us going to another topic, other topic. So this is a rough idea of the proof of the lower semi this part of lower semi continuity. Right. So yes. And here's another topic, the compactness. If we have further assumption, F is in some sense quadratic growth at space infinity, assume that V epsilon is bounded in this singular modica motor energy as epsilon j tends to 0, then there's subsequence such that some the limit is some xi in A0. So gamma convergence and compactness imply, under the same hypothesis of theorem 4, a minimizer of U epsilon is V epsilon subsequently converges some xi0 in the graph convergence, and xi0 minimizes limit energy. Furthermore, if xi0 equal to 1, if x is not A is anyhow the point where we add we square 0, we square A. And the E0A is P01. Where P01 is minimizer of 2GP plus P plus with P is in 01. So then if F prime V is V minus 1 is positive, F prime is monotone increasing for V is greater than 1, and if V is less than 1, F prime V is negative. Then G is convex, so that GP is P plus is strictly convex for B positive. In this case, the minimizer is unique, and if V is not 1, so that GV is V minus 1 squared, then everything is explicit. And you see the minimizer P0, 1 over B plus 1, and the limit energy is B over B plus 1. So this is exactly explained our example. Show with pictures, right? Limit energy of minimizer is B over B plus 1. And the value of the value at 0 is at A at 0 is just 1 over B plus 1. So this is our theory. It's very consistent with observation. So what is the singular limit of Kobayashi-Warren-Carter energy itself? So this is already discussed in the Kyoto U. And the limit energy is the following. Okay, this is a part. This is jump, right? And the lower stuff is important. Upper stuff is disappear. So this is one, and this is original total variation. And this is singular modica, or limit of singular modica motor part. Right. So this is JU denotes the set of jumps. Right. Okay. And topology is the L1 in sorry, L1 in U. Sorry, this is L1 in U. And the graph converges V. A higher dimensional case is more involved. Then we have to choose suitable topology. And this is I do not show today. But higher dimensional case is more involved anyhow. Okay. So we now discuss Kobayashi-Warren type energy and total variation. And EKWC is U Xi, and we take minimizing Xi minus. And Xi plus is just 1. Then the energy is just K gradient U plus J. J is jump of U, and this type of energy. And K rho is a minimizer of such kind of energy. And if F rho is rho minus 1 square, then K rho is rho over rho plus 1. Usual total variation TV correspond to the case K rho is equal to rho. So jump is just modulus of U plus minus U minus, but here jump is dominated by measured by this kind of things. So this means if the jump is large, jump is not contribute energy so much. If the jump is small, this contribute much. Right? So this is a energy. Kobayashi-Warren-Carter type total variation energy at the limit of as a minimizing Kobayashi-Warren-Carter energy by the variable Xi. And also, this is of course Kobayashi-Warren-Carter energy is quite different from usual TV since the large jump will come for TBKWC. We consider TBKWC with fidelity term, like Then this is of course discrete scheme of gradient flow. And here's the theorem. It's just one dimension. One dimensional case, let U be a minimizer of TBG in BV. Then you must be a piecewise constant. Minimizer must be a piecewise constant if G is continuous in AB. Moreover, the number of M of jump must satisfy. So this, in some sense, small jump, the energy dislike. Only big few jump is better. So in the case K rho is rho over rho plus 1, then K is strictly associative in the sense that K rho, this type. So for you, let C be a coincidence of G. So for minimizer U must be a continuous on C. Also, U must be a constant outside C. Here's one typical lemma. Oh, sorry, this picture is better. U be a non-decreasing minimizer of total variation K, Kobayashi-Warren-Carter, but with fidelity term G. And alpha, beta, gamma is coincidence set and ordered in this way. And U beta, these two jumps, the second jump is better than first jump. Assume there are no coincidence set in between gamma beta. Then beta minus alpha is strictly less than Cm over M, where M is a oscillation from of G. So this is the story, right? U and here there's no coincidence set in between. And here's the many coincidence set. In this case, we have an estimate for beta minus gamma. Beta minus gamma cannot be so close. Okay. So this is a rough idea. Since there's a no coincidence set in between gamma and beta, you have only one jump. We said V is a competitor. Then this energy is something like estimate, and we also compare fidelity term. Then since rho 1 is greater than rho 2, so let me go back. Rho 1 is this. Rho 1 is smaller than rho 2. We can replace rho 1, rho 2, and this yields total variation energy with fidelity G is such kind of things. The last parenthesis must be positive. That means must be non-positive. Non-positive, since U is minimizer. So we conclude that beta minus alpha as estimate. So, yes. So this is one key lemma for this argument. Yes. Okay, but I remark one thing. If we replace TBKG by total variation, then minimizer is no jump. If G no jump, if G has no jump. More precisely, G jump this quantity is always in between G. Or even we can say G minus such things. This is already observed by Bonforte and Figari. So, and many extensions, recent extension by Chambord and Caesar, arbitrary vector value. But anyhow, it's completely different. This jump set of the minimizer should be contained in the jump set of G. But here it's quite different. Even if jump G is continuous, there must be a jump, and even piecewise constant function. Moreover, the number of jump can be estimated by this constant by using Kachimo lemma. Okay, I don't think I have enough time, but let me go to the third topic, the singular limit of the Kobayashi-Warren-Carter limit gradient flow. So the problem is originally as a form. This is parabolic problem, total variation flow plus parabolic problem. And if v takes minimum, then such kind of step function, a Heaviside function, Heaviside type function is a solution. Yes, this is the meaning solution should be rigorously interpreted, but this is actually solution in a rigorous sense, which I do not explain. The equation becomes such kind of thing. For only U is just disappear, U is given, and always satisfies if we has a minimum at the center. And then the equation of V is here's I think this should be a plus. Plus is missing here, sorry. Reasonable scaling to extract solution is something like that. In the RIKEN equation, you have this way, but reasonable scaling to produce mean curvature is tau is epsilon tau star. So this is different scale. And consider this type of problem. Now it's become correct, right? And this is a delta function, and the Vx is equal. And what is the limit profile as V as epsilon tends 0? And this is, by the way, delta function. If x equals 0, it is expected that V tends to 1. Why? Because of this term. However, how about the behavior of this type? This is a linear problem, actually. And we will find the fractional time derivative. Tau 1 is equal to simplify the notation. Our equation is such kind of very simple equation, and this is a singular modica Mortora plus b with 0 square, right? So, and consider the gradient flow. We know already in the section 1 that E epsilon B SMS combines ESM 0 B as gamma combines and the graph converges. And the limit we know is B square 2G zeta in this particular case. And the G zeta is in particular case zeta minus 1 square. The limit equation is V tends to 1. Outside, we are interested in the limit of the center 0. The naive guess is, CT must be a gradient flow of E0B SMM, but it turns out this is wrong. What we discussed, what we have is if you consider this kind of equation with Neumann boundary condition with V0 epsilon, and if we consider very special data, which is well prepared in the sense that if there is a constant such that V0 epsilon tends to such kind of things. So this is in some sense one group, very sharp group. Yeah. Then our recent paper says let V epsilon be the solution of equation with Neumann boundary condition. Assume V0 is well prepared Then the graph V epsilon combines to the set valued function with the set 1x not is equal to 0 if that's 1. And there's a closed interval, xi of t1 for x tends 0 in the sense of House distance graph over this type of set. Well preparedness is not essential in this statement and can be weakened, of course, but the limit is something like that. And xi t satisfies, eventually satisfies such kind of equation. The function xi t must solve this type of equation. And this is not gradient flow. Or ds is unnecessary, by the way. So this is a convolution. And xi is 0 is 1 over c. And here ma is something like power function times exponential damping. If a is equal to 0, the left-hand side equals f01 half plus dxi dt, and this is nothing but Caputo half derivative of xi. So what is the structure of the problem? It's interesting, very simple. We consider just boundary solution of a heat equation with a Robamba type boundary condition. Assume that Wx0 C for some C. Initially, this is a constant. Then the value function, so it is initially constant. The value, boundary value must be satisfy such kind of Caputo type, half derivative of Caputo type and BW. So, and following the idea of carefully, Sylvester studied the minus Laplacian alpha is obtained at the Dirichlet-Neumann map of degenerate Laplacian. We are able to assume the similar things. So we have considered this one, and we obtain Wx is equal to dt eta. Eta is the boundary value, right? With gamma 2 minus 1 over 2 minus alpha. Here, C gamma is a positive, computable positive constant. And we found all such kind of half the fraction derivative, Caputo type fractional problem for any power, not necessarily half. This is a proof, and maybe it's better to skip this type of proof, but this is very simple. Just using Laplace transform with x, and then with t, but maybe t is missing here, sorry. Oh, no, this is okay. W is original equation, and take Laplace transform to t, and you get such kind of things, and then it's easy to calculate. Then we get such kind of derivative. This is the structure of the problem. So, first of all, so let us summarize what we say. We characterize singular limit of Kobayashi-Warren-Carter energy. This is discussed by our paper with Okamoto and Uesaka, and for a higher dimensional case, Okamoto, Uesaka, and Sakakibara paper. And all minimizer must be piecewise constant for the Kobayashi-Warren type total Bayes energy with fidelity, even if the original function is continuous. This is a more recent paper by GOS plus Kuroda and Kubo. We show in a very simple setting that Kobayashi-Warren-Carter gradient flow, the limit is fractional in time gradient flow. This is by Kobayashi, the same similar author with Uesaka. So this is almost end, and each part remains couple problems. But first part, higher dimensional case, we are able to prove gamma convergence limit as expected. However, compactness is still open problem. The second part is with fidelity term, the limit Kobayashi-Warren-Carter energy, Kobayashi-Warren-Carter type total energy has a tendency that its minimizer should be a piecewise constant. This is just one dimension. We don't know. We expect a similar thing for higher dimensional case, but we don't know. And the third case, gradient flow, we need some extension for more general setting. Okay, yeah, so far we fix you. Okay, I think the time is almost up. So thank you for listening. Thank you very much.